Hello Internet, my name is Quinn and this is Blondihacks. Today I'm going to make an unusual fixture. It's not something you might think you'd need, but once you start building models and other small stuff, it turns out you need to do this quite a bit. And that's cross-drilling wire and other very small diameter round things. I'm going to make a very special fixture to do that today, so let's go. Here's the fixture that I've designed and that we're going to build today. It's a little bit different than other cross-drilling fixtures that you might have seen for reasons that will become clear here momentarily. I modeled this with the smallest diameter wire that I hope to ever support with this thing, which was 80 thousandths. Let's compare with this much larger cross-drilling fixture you may have seen me make a couple of years ago. This one has a different design. It has a large hole in the top, and the idea is that your center drill and any drill sizes that you might want can all go down through that into the stock. This wire drilling fixture is different. The top clamp is solid and you actually drill right through it, so it acts as a drill bushing to support the drill as well as clamping the material. So I spit out some drawings from my CAD model and let's go to the scrap bin for some steel. This thing is so small that a tiny little corner of this one piece of scrap is going to be more than enough to make this entire fixture. For a sense of scale, this whole thing is smaller than my thumb up to the first knuckle, so it's very, very tiny. I'll start by rough cutting the two pieces over on the bandsaw. So there's a slightly larger base piece and then the thin top clamp, both of which will come out of the end of this one piece of bar stock. Next, I'll square up the base piece on the mill. I'm going to go through this in more detail than I normally would because this is a fixture. And on a fixture, care and attention really pay off. You want to be as precise and meticulous about everything as you can because any errors that are in a fixture will be translated into every part that you ever make with that fixture. Error is transitive in machining. After creating one reference face, I then pull the part out of the mill and completely clean up the setup, get rid of all the chips, make everything spotless once again, clean off the parallel. Again, meticulousness really counts. You want to squeeze every ounce of precision out of your setup. Then the machined surface goes back against the fixed jaw on the vise, and we can create our second surface. Between every cut, I'm also deburring every edge of every face. A piece of copper wire or something round like round bar or a ball bearing goes against the movable jaw to remove the influence of that jaw and make sure only the reference face against the fixed jaw is setting the orientation of the part. And always tap it down. We can create our second face. When you're first learning machining or when you're creating something that needs to be really accurate and precise like a fixture, then you need to go through all of these super meticulous steps. Once you're more experienced, then you can learn when you can skip some of these steps, but learn the rules, then you can learn when to break them. And you will need to learn when to break them because of course all of these meticulous detailed steps take time. Precision takes time and that's why precision is expensive. So you want to make everything in a hobby shop only as precise as it needs to be. In this case, as precise as possible. Now I have two faces that should both be flat and perfectly square to each other. Once again, deburr all four edges of every single face as we create them because burrs will interfere with seating the piece properly in the jaw and it's going to create taper and other errors. And once again, between every operation, take everything down and clean everything. Make it all spotless again. Make sure that a chip didn't find its way under your parallel or isn't secretly sitting on top of your parallel, just waiting for you to put your part down on top of it and create that half-thou taper that's going to wreck your fixture. Now we have a reference 90 degrees, so those two surfaces go back and down in the vise because that will reference the back fixed jaw and the bottom of the mill. And then once again, the copper wire on the unmachined face to eliminate the influence of the movable jaw. Machine that face. Now we have three faces that form a U shape, so now we don't need the copper wire. Those can go down in the vise, those three faces. Once again, of course, tap that down. Everything's deburred, everything's clean, and we can create the final face. At this stage, we have four faces around the long axis that are all parallel and square to each other and all flat. One face is going to get a V groove, and that axis I've left intentionally oversized on the part. You'll see why in a minute. But now we can go and do the ends. I like to end mill the short ends when squaring up stock. It's not technically as accurate as setting the piece up vertically and indicating it in because side milling always has some deflection in it. However, in my experience, the deflection created by doing this on small parts is less than you will get trying to indicate in a very small part and get it indicated perfectly vertical. There you go, one perfectly squared up block. This is a really good exercise to go through if you're new to machining and or new to operating a mill. It's a fundamental skill and it's also really satisfying. Now it's time for the V groove, which I'm going to do with the corner of an end mill. So I'm going to set the piece up at 45 degrees using an angle block as you see here. Now the trick with this method is getting the center of the V groove to land in the center of this face when you're done. It's actually fairly difficult to do this extremely accurately, and that's why I've left this face oversize. We're going to do our best to get this V groove in the center, but we've got extra width on this face so that if we miss, we can machine down one side or the other as needed to get the groove into the center, because it's much, much easier to align a flat face with a V feature than to get a V feature perfectly aligned with a flat face. I set out to explain this using a bunch of fancy graphics and math, and then realized actually I did all that in my previous cross-drilling fixture video, so I'm just going to slide that footage right in here and maybe the viewers won't notice. So buckle up for a little retro Blondihacks. The secret to this technique is that we're using the squareness of the end mill itself to create the perfect V. But that does mean we have to mill the stock at this funny angle, and that also means it's a little tricky to get the center of the V to land in the right place because we're milling the hypotenuse of that triangle. Now we can easily find this top edge by touching off with the end mill, so what we need to know is this distance here. How far down do we go so that we're milling the bottom surface of our V there, and then the side of the end mill is going to create the other surface of the V. Well, we know this hypotenuse distance, of course, because we know the width of our V slot and the size of the block, and it's centered on the block, so that's easy. And because this is all 45-degree angles, the right triangle that we're forming is isosceles, and so all of the other sides are the same dimension. So grade school trig, a squared plus b squared equals c squared. A and b have the same value, therefore to get z, we square c, divide by 2, and take the root of that. Finally, we need to know how far to mill on x. For that, we have another little isosceles right triangle in the V slot there. The depth of the V is the same as half the width of the V, so the x milling distance is just the V slot depth squared times 2 and square root of that once again. I was very shouty in that clip. Am I always that shouty in my old videos? If so, I'm sorry. And sweet metallic ore, what was I thinking with that font? Oh, those old videos are terrible. With that crucial depth value determined, now we need to move the end mill down that exact amount from that top corner, which means touching off on that top corner. I don't actually want to do that though because it's going to mess up that top corner, and touching off on a very thin corner is difficult because it's actually difficult to tell when the mill starts cutting. So a more accurate way to do that is to use a feeler gauge in this case. Bring that end mill down nice and slow until you get a light drag force on that feeler gauge. In this case, I'm using a 20 thou gauge, so then you move the end mill down 20 thousandths using the quill DRO past where it was, and now you know that mill is right on that top corner. Then we can move down from there the amount that we calculated and start cutting, making our passes inward, and the bottom of the end mill is going to create the bottom surface of the V, and the side of the end mill is going to create the opposite surface of the V. The only gotcha here is that because we're cutting into angled material, every pass, the cut is going to get heavier and heavier if you use the same X offset on each pass like you normally would when side milling. You actually want to reduce your delta moves on X after each pass in order to try and keep the cutter load the same on each pass. After side milling over the appropriate amount to create one side of the V, that is our final V cut. If we did our job right, then that should be perfectly centered, or at least very close. Here's how we're going to find out. Put a gauge pin in that V, doesn't matter what diameter the pin is, and we're going to put it on the surface plate and feed it under the dial indicator. And we want to touch off the indicator and then move the pin back and forth underneath it until we find the highest reading. So we have the high spot of the gauge pin. Then zero the indicator on that high spot. Next, flip it over. Again, same pin, same groove, but with the part flipped over on that axis. And if the groove is perfectly centered, once again finding the high spot on the pin, it should be at exactly the same reading. And it's not. It's actually off by about 15 thousandths, which is way more than I usually get when I do this. I think what actually happened is after I used the feeler gauge to find that top corner of the part, I forgot to actually move the quill down before starting to make my cuts. And then the other 5 thou of error is just me being bad, I guess. But that's okay. That's why we do this method of leaving this dimension oversized. This was definitely a carefully orchestrated mistake to show you the power of this method. Yeah, sure, that's it. While we're here, it's a good idea to check the ends as well. Make sure the high spot at each end of the pin has the same reading to make sure that the pin is straight, and by extension, the V groove is straight along the part. And in this case it is. I got the same reading in 3 places along that pin. So back into the mill, and I remove the amount of material on the side that was too thick, as shown by the indicator. Then back to the surface plate to see how we did. So this was the side that was reading 15 high, and survey says, oh, look at that, right on 0. Flip it around, double check the other side once again, and 0 there as well. We're within a couple of tenths at least of 0 on both sides. If you wanted to get even better than this, then it would be time to go to the lapping plate, but I'm really happy with that. That's going to be more than enough precision for this fixture. At this point, you can check the dimension of the block and machine some amount off both sides if the block is still too wide, but honestly, the actual width of this block doesn't matter all that much, so I'm going to leave it where it is. Back over to the mill then once again, and I can center drill and tap the clamping bolts, the little screws that are going to act to clamp the piece into the fixture. These are number 3 screw threads, again, to give you a sense of how small this fixture really is. It is tiny. The only hardware I had in this size were these brass cap screws, so I'll use these for now, but it would be better probably if they were steel. Next up is the top clamping plate, which I squared up the same way as you just saw. I'm not going to make you watch all that again. I'm going to set it up for drilling clearance holes for those clamping bolts that you just saw. These are just clearance holes, and they don't have to be super accurate because they're only supplying clamping force, not alignment. That's very important. Speaking of alignment, now we can work on that. So I'm going to clamp the 2 pieces together and get them nice and aligned using the top surface of my vise to make sure everything's perfectly aligned as clamped. And we're going to clamp it in the vise with these 2 pieces together, and we're going to drill for some alignment pins. Speaking of which, we're going to have to make those pins first. I've got some drill rod for this, which I cut into 4 tiny, tiny little pieces, which I'm going to face down to a nice accurate length. Drill rod is great for this kind of thing. It's precision ground, so it saves us making all of these tiny little pins. To get them all to an accurate length, I face one end and chamfer so that we can get an accurate measurement later. Then flip the piece around, face the other end, and chamfer it again, and now we can take a proper measurement, and that will tell us how much more material to remove to get them down to the accurate length. Once again, similar to squaring up stock, when you're aiming for precision, you don't want to skip any of these little steps. Even though it seems tedious to face and chamfer 3 times, one of those times is just so you can take a measurement and then put it back in and then cut off that nice faced and chamfered surface. You have to do all of that if you want to get a very accurate length. And there's the result of our extra labor. That is dead nuts on length. And all 4 of them came out within a tenth of perfect length. So you see, the effort pays off. Clamping up the assembly in the mill now, I'm going to put a piece of paper in here because the 2 pieces, even though they're the same size to within a couple of tenths, 2 pieces clamped vertically in a vise will never both clamp equally. No matter how identical you think 2 parts are, physics laughs at your micrometer. So the piece of paper takes up any slight variation in the width of those 2 parts and makes sure that they both get clamped. Now I'm centering up with the edge finder, however, I have to make sure to edge find on the piece and not the vise jaws, as you might be tempted to do because that piece of paper is in there, and if you edge find on the jaws, you're going to be off center by half the thickness of that paper. I had to cut away a little bit of the paper to access one side, but now I can edge find on the piece, and I know that all of my alignment pins will be properly centered. They all get center drilled and drilled undersized slightly because they're going to be reamed for those alignment pins that we made. Once again, pulling out all the precision stops for this one, I've got 3 reamers that I'm going to be using. I've got my nominal size, and I've got an over-under reamer pair. These are 1 thou under and 1 thou over the nominal size of 1/8 that I want for these pins. These pins were made with drill rod, but drill rod, as good as it is, does have a tolerance of about 5/10 on it. So they're not necessarily going to be perfect. Well, the first one was perfect. That one is dead nuts. I measured all 4 pins, and as it turns out, all of them were dead nuts, so I happened to cut these out of a really good section of that drill rod, but it's not unusual for them to be a few tenths over or undersize. Now to ream these holes, I start with the undersize reamer, and I go through with this, and then I will test fit my pins after this. And that does not want to go in. It's close, but it's not going to go in. So that's actually good. It means the undersize reamer cut on size. If that reamer had cut oversize, we'd still be okay. That pin would be a perfect fit. However, now I can go up 1 size to the nominal reamer and cut again with this one. This does 2 things for us. Again, if the undersize reamer had cut a little oversize, which sometimes they do, then if the hole would have been perfect. Otherwise, when we go to the nominal reamer has almost no work to do because it's only cutting 5/10 off every side of that hole. It's only enlarging it by 1 thou. So that means because it's doing so little work, it's almost guaranteed to cut perfectly on nominal size. And survey says, whoa, look at that. That is a perfect push fit, and there is no play in that at all. That's beautiful. Now, if some of our pins had been a little oversized, then at this point we could go to the oversized reamer if the nominal reamer had still not cut large enough for those pins. There you go. The 3 reamer technique, if you will, is a way to get perfectly sized alignment holes for pins made from drill rod. Let's take those fixturing screws out now and see how the pins work. Yeah, there is 0 play in that at all. And this is important because remember, unlike the big fixture, the top clamp in this is also acting as a drill guide. So it has to have repeatable and accurate alignment between the 2 pieces of this fixture. We can't rely on the fixturing screws to do that, those clamping screws. They aren't going to align accurately enough to drill tiny holes in tiny pieces of wire. So these alignment pins are crucial. I'd like to keep this fixture for a while, so I'm going to cold blue it to prevent corrosion. First step for me for that is to clean everything, degrease it thoroughly in acetone. I'm trying a different cold bluing product than I normally use. This is Birchwood Casey's Super Blue. My go-to is Brownell's Oxbow Blue, which I really love, but I ran out of it. I'm not able to get it locally, and I didn't want to wait for shipping, so I got this stuff. Let's give it a try. This is literally my first time ever trying this stuff in real time on camera. Here you go. And first impressions, it's not great, I gotta say. It's not going on nearly as nice as the Brownells does. It's very blotchy. It's also much bluer and less black. Some cold blue compounds work better if you immerse the parts, like Jack's Metal Blackener, for example, works much better with immersion rather than rubbing it on, so I tried that as well, but didn't really make any difference. Now, I don't want to judge this stuff based on one use. Maybe it wants different prep steps than I usually use for the Brownells, but using the same process that I like for Brownells did not work very well for the Super Blue. Well, I ordered more Brownells, but for now this will work, I guess. And of course the last step with cold bluing is always to oil the surfaces, and that seals everything up, makes sure that the corrosion stays away. Now to make those alignment pins permanent, I'm going to use Loctite 680. 603 would also, I'm sure, work here, which is my usual go-to, but technically these pins are slip fit and 680 is the right application in this case. So wipe off the excess, and then I gave that Loctite a full 24 hours to cure. Hopefully it still fits together after the pins have set, and yes, that looks very good. The alignment is very close, which means you have to have it perfectly level when you move it up and down or it will bind, which is to be expected. But that's a good thing. That means, again, the alignment of those pins is very, very close, and this fixture is going to be very repeatable and very accurate. Because once again, there's no margin for error when you're drilling tiny, tiny holes in tiny pieces of wire. On the subject of cold bluing, here's a random selection of tools that I've made and cold blued over the years. I've done a lot of cold bluing, previously with Jack's and Brownell's Oxbow Blue, and I gotta say, I know they all kind of look the same on camera, but in person you can really see the difference. The stuff that was done with Brownell's just looks way better. The stuff done with Jack's looks a little bit worse, and I'm afraid this Birchwood Casey stuff is a distant third, but we'll press on. Alright, let's give our little steampunk Lego brick a test run and see if it will actually do the job for which I've hopefully designed it to do. Here is a piece of 304 stainless wire. This is 100 thou in diameter, and I would like to drill a perfect 52 thou cross hole in it. Before I drill, I want to verify the alignment of the V-groove with the top piece. because that will make sure that the V-groove is properly centered in the base and that my alignment pins to the clamp are doing their job. So I edge find centering up on the clamp piece, and I put that in the absolute scale on the DRO. Then I edge found on the wire and put that in the incremental scale. And you can see that they're within 0.8 of each other, which is frankly within the error bars of mechanical edge finding anyway. So that's effectively perfect for the hobby shop as far as alignment. So that's good. That means I can trust edge finding on the fixture, and I don't have to necessarily edge find on the wire itself, which may or may not be available. Okay, time to drill our first hole. The way this works is, for a given hole diameter, the first time you drill it, you drill right through the top clamp, creating the drill guide, and through your workpiece. Then from then on, if you want to use the same drill, you use the existing hole as a drill guide. And there's room on the top clamp for many different sizes of hole. This being steel, it will hold up to many hundreds of holes, which is more than enough for a hobby shop. You don't have to harden anything or make hardened insert bushings or any of the very fancy things that people might think that you need. All right, moment of truth. Let's get the workpiece out and see if we have success. And would you look at that? That looks like a perfect 52 thou hole, dead center on a 100 thou piece of wire. Very pleased with that. Really, I can't find a single thing wrong with that, so I think this fixture is a success. I'm going to get a lot of use out of this, making handrails and other detail pieces for model parts. If you have a need to drill tiny cross holes in tiny pieces of round bar, maybe this will help you too. I hope you've enjoyed the process, and maybe you learned something in here about some techniques for making really accurate and precise fixtures on modest machinery like most of us have in our hobby shops. You can do it with clever order of operations and a little bit of forethought, and you don't have to have a surface grinder or a lot of other high-end machinery just to make accurate fixtures. Thank you very much for watching. I hope you found this interesting. Thanks to my patrons for keeping all this content going, and I will see you next time.